Okay. In the earlier session, we had focused on the VAR based on a normal distribution returns, right? But in most general scenario, what we observe is the VAR, the returns, they do not follow a normal distribution. For some of the scenarios being because of the interest rate fluctuation, because when we have taken the asset returns, asset in this case we have taken as a stock. So the asset returns are, if everything is stable, let's say the interest rates are stable during the entire period, let's say the political situations are stable during the entire period, then there is a good possibility that the returns will follow a normal, or probably if the company conditions are also stable. Because in the Infosys case, why did we find a non-normality? The day the results were announced, there were some specific poking events, right? The day when the results were announced, the expectations were completely different and the realities were completely different. So because of that, there was a huge fall or huge increase in the price on those days. So because of some of the things like interest rate volatility changing in the economic or the political scenario, we see some of the days the returns will be either too high or too low, and that weirdness will cause the values to deviate away from the normal distribution. So what is being said is, you should make sure that your model, that is where the complexity is coming up. If I know with just by removing 2 3 values I can ensure the normality of the data, then probably we will still incur those extreme values, right? When in the last 250 days there were 3 or 4 days which had those extreme values, which means there is a 2% chance or 1% chance that those extreme values are very much possible, right? So that is where the models are talking about how do you incorporate even those kind of things to build up your VAR more and more comfortably. How do you incorporate even those kind of data, which means my data is becoming fat tail rather than a normal tail. When I say fat tail, probably the chance of observing, see, as per normal, the chance of observing, let's say the data beyond this point, if I'm assuming that beyond this is my tail, the chance of observing beyond this point, let's say, is 1%. But when I'm talking about a fat tail, the chance of observing beyond this point, the same point, beyond this point, probably is 2 or 2.5% or 3%, depending on how fat the tail is. Right? The chance of observing beyond a certain point will either increase or decrease. So we have to make sure how do we address those kind of fat tail scenarios and come out with a much better definition of the VAR. And in that also, if the fat tail occurs towards the right, no one is bothered about it, right? Probably there is instead of saying there is a 1% chance that your daily gain is more than 500 bucks, if someone says there is a 5% chance that your daily gain is more than 500 bucks, no one is bothered about that statement at all. Whereas as a risk manager, my focus comes on the negative side of the tail. When I say there is 1% chance that your loss will be more than 500 bucks, versus if it is a fat tail, I may have to say there is a 5% chance that your loss will be more than 500 bucks in a single day. Then that is more and more alarming. So that is where the negative side is the primary focus for any kind of a risk manager. And whenever we are designing those things, the instability of the model parameters, we have found out the mean, we have found out the standard deviation. If they are not stable, very much possible in even in our earlier when we talked about our Garsh model, our EWMA model, where we were estimating the volatility in the data, we have seen that at different points in time, the volatility is different, is getting differed. right? If the volatility is different, means standard deviation is differing. So the model parameters are not stable. In some period, probably the volatility is much lesser. In some period, the volatility is much higher. And because of that, if I am taking everything as a package, the 250 days data, see what did we do here in this example? We while computing the VAR, we have taken all the 250 days data, found out the mean, found out the standard deviation based on all the 250 days data. But in this, probably this is changing with time, this is changing with time. If these two are changing with time, this is what we are calling as instability in the parameters of the model, right? Probably if it is a very minute change, nothing to worry. But just with adding of one additional data, if these numbers change quite drastically, then that is where we are talking of instability, and even your assessment of the VAR will become more and more unstable. That is where even that where the volatility changes at different points in time. Let's say in the month of Jan, the volatility is much lesser, but from February to April it was higher, or from the next 2 months it will be much lesser. So if I am having such kind of variations in the volatility across the period, which was very clearly identified through your GARSH or EWMA kind of model, if you are finding that the volatility is changing across different periods, that is what is contributing to the fluctuation in the returns altogether. Because during this period, the volatility is much lesser. So any return will lie only between this and this. The worst case versus the best case return will lie only in a very narrow range. But if the volatility was very high during certain periods, probably your returns are lying between this and this, a very high margin. Now, if I am taking the whole thing to find out the mean and the standard deviation, it may so result in fat tails coming into picture. Because of some days being very narrow, some days being very broad. If I am considering all of them together, there is a very huge possibility of non-normality getting existed in the data. And that is why they are saying, and that scenario also we have discussed, we have used the word earlier also, that scenario is what we call as conditional heteroscedasticity, wherein the variance is different at different points in time. At different points in time, or for different variables of different values of x, here x is time for us. The dependent variable is time for us. For different points in time, if the variance is quite drastically different, low at this point, high at this point, we associate that scenario as a conditional heteroscedasticity scenario. Wherever we are observing such kind of a conditional heteroscedasticity existing, right? Probably on this data, if I just want to showcase that for you, probably let's say I'll take